Okay, so we discussed problem 1 and some definitions in the previous video. Now we'll continue with problem 2. So I already derived the expression for eigenvectors and eigenvalues for a square, and then for the matrix in problem 1 we also got the eigenvalues corresponding to a square. Okay, so now let's look at the second part of the problem. So now for A inverse, so consider the basic equation once again, which was AX equals lambda x. Now this time we'll pre-multiply by A inverse on both the sides. So as you can see, A inverse times AX equals A inverse lambda x. So on the left hand side of the equation, A inverse times A becomes the identity matrix, and identity matrix times X is X itself. So the left hand side is just X. And on the right hand side, once again, we factored out lambda because it was a scalar. So we have lambda times A inverse x. So now all we have to do is we have to divide by lambda on both the sides. So this gives us A inverse x equals 1 over lambda times x. And we can write that as lambda to the power of -1 or lambda inverse times x. So all we have to do is we have to reciprocate lambda in order to get the eigenvalues for A inverse. And once again, the eigenvectors for A inverse remain the same because, as we can see, x did not change, x is just the same. So based on the previous question, we had the eigenvalues 1 and 3. So now we reciprocate those two eigenvalues, and we'll get 1 and 1 over 3. And we get the same eigenvectors derived in problem 1. Now for the next part, we have A plus 4 times I, and we need to find the eigenvalues and eigenvectors for this matrix. So at this time, we'll add 4 times the identity matrix times the vector x on both the sides. So we did that. We added 4 times I times x on both the sides. On the left hand side, we factor out x, leaving A plus 4 times I. So remember, we cannot get rid of the I because A is a matrix and 4 is just a scalar. We cannot add a matrix and a scalar. If we want to add something, there should be two matrices with the same dimensions. So that's why we keep the I in this case. So it's A plus 4 times I. And on the right hand side, when we factor out x, we have already multiplied I with x, making it just x, because identity matrix times anything gives you that same thing, right? So we have that x, and we factor out x, we get lambda plus 4. And because lambda is a scalar, that's why we did not factor out identity matrix keep the identity matrix inside. So we get lambda plus 4. So this should tell you that the eigenvalue in this case should be lambda plus 4, while the eigenvector is the same x. So the eigenvector did not change, but now the eigenvalue is lambda plus 4. So lambda 1 was 1, so we added 4 to it. So now the lambda for the matrix A plus 4i is 5, and the lambda 2 in this case is 3 plus 4, which is 7 in this case. So we can generalize this property as A plus n times I x equals lambda plus n times x. So then the eigenvalues of A plus ni will be lambda plus n. So you can generalize this result by the same argument for any real n. So moving on. So now let's move on to problem 3. Compute the eigenvalues of this matrix and verify that the trace of A equals lambda 1 plus lambda 2, and determinant of A is lambda 1 times lambda 2. So let's consider the matrix A minus lambda I. That's always our first step, and then we find the determinant of that matrix. So we found A minus lambda I, and then we took the determinant. So because it's a 2 by 2 matrix, we just use the direct formula. We multiply the diagonal entries and subtract it by the product of the off diagonal entries. So this gave us, after simplification, we got lambda squared plus lambda minus 6. And now we'll follow the same procedure. We'll solve the characteristic equation lambda squared plus lambda minus 6 equals 0. we split the middle term lambda, 3 lambda minus 2 lambda, so that the product of those two middle terms gives us negative 6. All right, we split the middle term in such a way that the two middle terms have a product equal to negative 6. So because this is possible, we now factor out lambda from the first two terms and factor out negative 2 from the second two terms. And we get the factorization lambda minus 2 times lambda plus 3. So this tells you that lambda 1 equals 2 and lambda 2 equals negative 3. These two are the two eigenvalues of the matrix A. So next step is to find the trace of the matrix A and verify that the trace of the matrix A equals lambda 1 plus lambda 2. By definition, trace of a matrix is the sum of the diagonal elements of A. So in this case, the trace of A is negative 1 plus 0, which, those are the two diagonal elements, and we just sum them up and we get negative 1. So, and now let's check the sum of the two eigenvalues. So we got the two eigenvalues as 2 and negative 3. We sum them up and we get negative 1. So this verifies the property that the trace of a matrix A equals the sum of the two eigenvalues. So now we find the determinant of A and verify that determinant of A is equal to the product of the two eigenvalues. So we find the determinant of A just by the way of finding a determinant for a 2 by 2 matrix. We get negative 1 times 0 minus 2 times 3, which gives us negative 6. And now we take the product of the two eigenvalues, which gives us 2 times negative 3, which is negative 6. Therefore, determinant of A equals the product of the two eigenvalues, lambda 1 times lambda 2. So in general, we have a general formula for this. If a matrix which has n by n dimensions has n eigenvalues, then the trace of the matrix A is the sum of all the eigenvalues, and the determinant of the matrix A is the product of all the eigenvalues. So this actually comes in handy at times. If finding the determinant of a matrix is not that easy, we can actually use these properties in order to get the other eigenvalues. Okay, so moving on to problem 4. So we are given a matrix and we need to find the eigenvalues and eigenvectors. So what's different in this problem? The only thing that I found different was that first of all, it's a 3 by 3 matrix, and the second of all, we see that if you see the rows of this matrix or the column of the matrix or the columns of the matrix, you can see that this matrix has rank 1 because you can express each and every column or each and every row using one row. So suppose I take the first row, which is 2 comma 1 comma 2. I multiply that by 2, I can get the second row, and the third row is the same as the first row. So I can actually obtain two of the rows using just one row. So this tells you that it has rank 1. So consider the matrix A minus lambda I and then find the determinant of A minus lambda I. So again, as I told you guys earlier, that for A minus lambda I, we just subtract the diagonal elements by lambda and we keep the off diagonal elements unchanged because we are subtracting for a matrix which has zeros in the off diagonal entries. So determinant of A minus lambda I, so I use the cofactor method to find the determinant of A minus lambda I. So all I did was I just took the first row of the matrix and considered the first entry of the first row, which is 2 minus lambda, and then I deleted the first row and the first column and multiplied it with the first cofactor we got. So the first cofactor are the bottom 4 entries on the right of the matrix, which gives us 2 minus lambda, 4, 1, and 2 minus lambda. And now for the second entry, I have a negative 1 because this entry is in the first row and in the second column. So if we add the two entries in the index of the second element, which is 1 and 2, first row and the second column, that gives us 3. So 3 is an odd number. So because it's odd, we add a negative sign with the 1. And we take the determinant of the second cofactor, which is obtained by deleting the first row of the matrix and the second column of the matrix. So that gives us the second cofactor. And for the third entry, so this is in the first row and third column. So the index is 1 comma 3. If we add the two entries, we get 4. 4 is even, so that should tell you that we have a positive sign and not a negative sign. So we have plus 2 times the third cofactor, which is obtained by deleting the first row and the third column. So that would give you the third cofactor. So now taking the determinant, so the remaining determinants, which are in the form of 2 by 2 matrices, this is just these are just obtained by using the direct formula, and after simplification we get negative lambda square times lambda minus 6. So I would recommend you to practice this problem and check if you're getting the same answer. So solve the characteristic equation negative lambda square times lambda minus 6 equals 0. So it should tell you that the lambda squares correspond to 0. So the lambda square consists of two roots and both are 0. So we get lambda equals 0 comma 0, and then the third root is lambda minus 6 equals 0, which should give you lambda equals 6. So lambda equals 0 comma 0 comma 6 are the three eigenvalues of A. So one of the first two eigenvalues are just the same, so I denoted them by lambda sub 1 comma 2 equals 0. So the first two eigenvalues are denoted by lambda 1 comma 2, and the third eigenvalue is lambda 3 equals 6. So the next step is to find the eigenvectors. So all I do is I plug in the first eigenvalue lambda 1 comma 2 equals 0, and then solve for x. So as we notice that x is in the null space of A minus lambda 1 comma 2 I, as we have A minus lambda 1 comma 2 I x equals 0. So to find x, we have to obtain the special solutions of x in order to get the eigenvectors of the matrix A minus lambda 1 comma 2 I. So this is just like the earlier problem, but this time it's a 3 by 3 matrix. So as lambda 1 comma 2 is 0, we just plug in 0 in place of lambda, and we get the same matrix, which is the matrix A, because the eigen value is 0 in this case. Now we follow along the procedure to find the special solutions. So we do the operation row 3 minus row 1 and row 2 minus twice row 1, and we see that we only have one pivot variable and the other two are free. So we take u1 as the pivot or leading variable and u2 and u3 as the free variables. So let u2 equals t and u3 equals s. So then we see that twice u1 equals negative t minus 2s, and then we divide by 2 on both the sides, we get negative 1/2 t minus s. And then, as we assumed, u2 equals t and u3 equals s. So we just plug in these three values in the matrix X, and then we see that we get two special solutions. And so that makes sense, because as you can recall that lambda 1 comma 2 are essentially two zeros. They are two of our eigenvalues and both are the same numbers. So each and every eigenvalue should have a corresponding eigenvector. So in this case we obtain two eigenvectors, and that makes sense. So x1 and x2 are our two eigenvectors. So now for the third eigenvector, we plug in lambda 3 equals 6, and we follow the same procedure. Instead of lambda, we'll add 6 in the matrix A minus lambda 3i times x. So we get in the diagonal entries we get 2 minus 6, and the off diagonal entries remain unchanged. So 2 minus 6 is negative 4, and the diagonal entries in this matrix are all negative 4s. So we follow the same procedure and we reduce this matrix into a reduced echelon form. We do the matrix operations. As you can see, in the end we get the third row is a bunch of zeros, and we only have two pivots. In this case we have -4 and -3 as the two pivots. So now we solve the system, and here u1 and u2 correspond to the two pivot variables, and u3 is free. So I guess I made an error here. No, so u1 is not free, u3 is free. So I'll make that change in the slides. So yes, in this slide I haven't made that mistake. So -4 u1 plus 4t is 0, and -3 u2 plus 6t equals 0. So we solve these two equations, we get u1 equals t, u2 equals 2t, and u3 equals t. So now we can take t, we can factor out t, and we'll get 1, 2, and 1. So this gives us the third eigenvector, or the special solution of a minus 6i, and which is the eigenvector corresponding to lambda 3 equals 6. So 1, 2, 1 is the eigenvector of a for lambda 3 equals 6. Okay, so the final problem. So in this case, we follow the same procedure for finding the eigenvalues. It's just the minor difference in this thing is that we encounter imaginary or complex eigenvalues. So let's see how we tackle that problem. So first step is to find the matrix P minus lambda I and the determinant. So in this case, I instead of using the cofactor formula, I use the pivot formula in order to find a determinant. So I took the matrix P minus lambda I got the matrix negative lambda 1 0 0 negative lambda 1 1 0 negative lambda. So I thought that it's easy to convert this matrix into an upper triangular matrix because there's just one entry in the third row and the other two entries are a bunch of, so the first entry in the second row is 0 and the second entry in the third row is 0. All I had to do is change the third entry in the first row, which was 1. So I did the row operation R3 plus 1 over lambda R1. So I got rid of the first entry in the third row, but then it changed the second entry of the third row, so I had to get rid of that as well. So I did another row operation. So in the end I got negative lambda, and negative lambda cube plus 1 over lambda square as the three diagonal entries. So in the end, all I had to do is take the product of those three diagonal entries, and that would give me the cubic equation, which is the characteristic equation once, and then we'll have to solve for lambda. So I would, in most of the cases, I wouldn't recommend using the pivot formula, but I thought it was easy in this case because we just had to get rid of one entry, but then it caused problems later, and then I had to do another row operation. So I would recommend you guys to use the cofactor formula, or if you're comfortable with matrix operations, it's not a bad idea to use the pivot formula, but in most cases it's better to use the cofactor formula. So now the step 2 is to find the roots of the characteristic equation of determinant of P minus lambda equals 0. So we solve negative lambda cube plus 1 equals 0, and in order to do that, so there are two ways of dealing with this problem. First of all, we identify that lambda equals 1 satisfy the above equation, hence lambda 1 equals 1 is one of the eigenvalues. So if you plug in lambda equals 1, we get 0. So that should tell you that it satisfies the equation. So lambda 1 equals 1 has to be one of the eigenvalues. So now you have two options. One option is to factorize lambda minus 1 out of lambda cube minus 1 using the long division method. You can do that if you want to, but I used another property which is a cubed minus b cubed. So I use the general formula for this property. So it's a cubed minus b cubed equals a minus b times a square plus ab plus b square. So here I took a as lambda and b as 1. So I did this factorization and I got lambda minus 1 times lambda square plus lambda plus 1 equals 0. So that tells you that one of the roots is lambda equals 1, and the other two roots would be found out by solving the equation lambda square plus lambda plus 1 equals 0, which is the second part of the product we obtained. If you want, you could use long division and you'll get the same result. You can verify that. So now we need to find the other two roots. So we found the first root as lambda equals 1. To find the other two roots, we need to factorize the equation lambda square plus lambda plus 1 equals 0. And we'll use the quadratic formula for that, because there's no easy way of finding the roots. You cannot split the middle term and obtain the two roots in this case. So we have to use the quadratic formula in this case. So if we have an equation of the form a lambda square plus b lambda plus c equals 0, the quadratic formula is given as lambda equals negative b plus minus the square root of b square minus 4ac over 2a. So I plug in all the values. In this case we have a equals 1, b equals 1 and c equals 1, because a, b and c are the coefficients of the equation, and all the coefficients are 1, and the constant c is also 1. So all I have to do is I just need to plug in 1s in a, b and c in the quadratic formula. So after doing that, I got a negative 1 plus minus square root of negative 3 over 2. So I factored out square root of 3, and we have square root of 3 times square root of negative 1. So as we discussed earlier, so the hint was to take I equals negative square root of negative 1. I just replaced the negative of the square root of negative 1 with I, and that's it. And that should tell you that it's a complex root, because square root of negative of 1 does not fall on the real line. It's a complex number. So we replace that by I, which is a complex number. So the two roots are given by negative 1 over 2 plus minus square root of 3i over 2. So now the first root was lambda 1 equals 1. The second root, we took the plus sign in this case. So that gives us negative 1 over 2 plus square root of 3i over 2. And then the third root would be taking the negative sign instead of the plus sign. It gives us negative 1 over 2 minus square root of 3i over 2. And that's all for this section, and I hope you guys understand the problems. If you have any questions, you can discuss it with your TA. Thank you.